morning, everyone. I hope you are all recovered after the party yesterday. I still think it was amazing. I will remember it for many years. If you haven't been there, you can watch Dylan's stuff on YouTube later. So this is a talk on debugging and profiling .NET Core applications on Linux. And I think that some of you don't yet have .NET Core applications running on Linux. But this is something to consider if you will at some point deploy .NET apps on Linux. If you want to know what the diagnostics story looks like, if you want to know what to do if you will need to profile, to investigate performance issues, to analyze core dumps, this is the talk for you. And if you're using .NET Core on Linux today, hopefully this will give you some ideas and tools and show you what things are possible. So my name is Sasha. I work for a training and consulting company called Sela. I'm based in Israel, and I like coming to DotNext often. I'm also on the program committee, so I'm deeply invested in this conference, and I really enjoy it very much every time. So this is the plan for today. First of all, it's pretty crazy, I think, that we got to the point where we can actually talk about debugging and profiling .NET applications on Linux. This is, like, in the first place, pretty incredible. And the plan for today is to give you 5 things, to give you 5 takeaways from this talk. One is profiling CPU activity, figuring out where the CPU time is going. 2 is visualizing this information using flame graphs, which is something on Windows we're not exactly used to. But on Linux, flame graphs are a really useful visualization method, and we will apply it multiple times throughout the talk. We'll see some of the Linux tracing tools and how they can be used with .NET Core applications. In many cases, the same tool works exactly as is. We just need a little bit of information from the .NET runtime to make that tool useful for .NET processes as well. We'll talk about what I call here .NET Core runtime events, such as garbage collections, JIT compilation, assembly loading, all these low-level events coming from the CLR, and how to capture them and visualize them as well. And finally, we'll talk about core dumps, which is more or less the only way to do production debugging of .NET processes on Linux today. So we'll see how to create and analyze core dumps. Just one disclaimer before we get started. Some of this stuff is changing. .NET Core is still under rapid development, even though we are talking about .NET Core 2.0, and everything I'm showing you here works with the latest build. But tomorrow something could change. Don't blame me. Check out the documentation, check out online sources for more information. And some of this actually relies on scripts that I hacked together just to support my demonstrations. So in terms of operating systems, just to give you, some parallels with other platforms to explain what we're looking at. So we'll see how to do CPU sampling, which is something that on Windows can be done using ETW as well as other tools. We'll talk about dump files, which we also have equivalents for on Windows. We'll talk about dump analysis. So really, the scenarios are more or less the same. The difference is just the tools and how to apply them and various quirks along the way. So this is a talk on the Linux side of things, but these things can absolutely be done on other platforms as well. Before we get started, just a bit of theory and an important mention about overhead. Some of the tools I'll be showing you today need careful management, so you don't collect too much information, so you don't end up with very large trace files, so you don't spend a lot of resources and slow down the system just by running the performance tool. So make sure you keep in mind the overhead, and I'll address it once or twice during the talk. And the second thing I want to mention is the distinction between sampling and tracing tools, which will come up during the presentation. When we say sampling in the performance profiling context, we mean looking at samples of what the system is doing over time, not tracing every single thing that's happening, but looking at samples at predefined time intervals, for example. Looking at the system every 10 milliseconds and seeing what's happening. We use sampling for really high-frequency events, where we can't record every single event, so we have to use some sort of statistical sampling. And tracing, when I'm going to say tracing in this presentation, I mean actually recording every single event, recording every occurrence of the event, and then analyzing it later or processing it in real time. So that's just, again, terminology. So let's start with the official story. Like, how does Microsoft expects us to diagnose performance issues with .NET applications on Linux. These are the different performance information sources we have available. And there is a tool that we'll look at very, very briefly, which can collect information from a lot of these sources. So starting very high up top, in the .NET application itself, you have access to the event source API, which is also available on Linux, for emitting various kinds of profiling information, events basically. On Windows, these would be ETW events. On Linux, we don't have ETW, but we have something similar, which we'll talk about later. Then underneath your .NET applications, we have the CLR itself. And the CLR has a bunch of interesting events as well, for garbage collections, assembly loading, monitor contention. There's a bunch of interesting things we can collect and analyze and record. Then at the library level, operating system libraries, the kernel itself, Linux has a lot of stuff to offer which is not .NET specific anymore. And we'll see examples of that as well. Tracing things like disk accesses, understanding context switch latency. These are things that we can do at the OS level, not even specific to .NET applications at all. And on the very bottom of everything, we have the hardware as well, which provides interesting performance information. So the CPU, modern CPUs, are equipped with lots of performance counters for things like cache misses, branch mispredictions, and of course, all this information can be used with .NET apps as well, and on Linux specifically. So again, the official story. How do you use all these various performance sources on Linux? Microsoft provides a script called perf collect, which is capable of recording various kinds of performance information on Linux and then analyzing it later. So here's how it would work. You download that perf collect tool. It's just a bash script. There's no dependencies you have to install up front. And then perf collect helps you install all the prerequisites you need on your specific distribution. So it downloads and installs everything you need for the actual data collection. And then you run perf collect, and you collect performance information. That would include CPU usage, GC activity, a bunch of other events, and you can slightly customize what actually ends up collected. And here's where the story turns a little sour, in my opinion. At this point, you're supposed to take the result of the recording and copy it over to a Windows machine, which is where you use perf view, which I hope some of you are already familiar with. I've done a talk about it at one of the previous conferences. And you open the trace file in perf view and view the results. And even though some performance work can actually be done on the original Linux system, it definitely looks like, if you check out the documentation, that this is the workflow you are supposed to follow. And I have multiple problems with this. Among other things, you don't always have a Windows machine that you can copy the trace file over and so on. But also, I want to understand what's happening. I want to understand how this script works. I want to understand exactly what is collected. I want to have full control over the events we are recording so that I have control over the overhead as well. So we're not going to use perf collect in this presentation. You can absolutely check it out. It's quite easy to get started with. And perf view itself has great features for opening these result files. But this is not what I'm going to use. I'm going to start from basic principles. And on Linux, performance investigations usually begin with the perf tool. And perf is a multi-tool for doing various kinds of performance work on Linux. Among other things, it can sample CPU usage, it can record disk accesses, it can record network events, it can record pretty much any performance-related activity on a Linux system. And what's even nicer is that it is developed as part of the Linux kernel. So it's available on all the different distributions, and if it's not available, you can build it from source. It's a tool that you can always use on Linux. And it's designed for production use. It doesn't have a UI, God forbid. It doesn't have any complicated dependencies. You can use perf pretty much everywhere, including on production systems. So here's how perf works more or less under the covers. Perf is a kernel mechanism, and there's a bunch of different things, events, that can feed into the perf infrastructure. And that includes things like low-level CPU events, cache misses, branches predicted, instructions, and so on, page faults and higher-level software events, scheduler events like threads moving from one CPU to another, context switches, that kind of thing, even higher-level stuff like file accesses, and you can also use perf for tracing user space stuff, such as memory allocations in an arbitrary program through the malloc call, or any other function in user space, essentially. And then what happens is all these different events feed into this perf events infrastructure in the kernel, and then they can go into a file, which you can analyze later, or into memory buffers, which you can analyze in real time. But most users of perf, they record to a file and analyze later. There's not a lot of tools that actually do real-time analysis. And the perf collect approach I was telling you about over here, it uses a file. So it records a lot of events into a file, and then you can open that file elsewhere and analyze the results. And that in itself produces a certain overhead. If the rate of events is very high, you're going to have lots of disk activity to write these events into a file, and it will be expensive to open the recording as well. So a little later, I will show you an alternative which doesn't rely on files, which doesn't require recording every single thing into a file for analysis. So this is the perf story. And before we can analyze the results, before we can analyze any kind of recording of a .NET process, we need to talk about a little something that is always a pain, especially with dynamic languages that get compiled at runtime, like .NET, and that's debug information, or symbols. So on Windows, you're probably familiar with symbols, PDB files, right? On Linux, there's a similar story. If you want to see function names in your recording results, in your analysis tools, you will need debug information. You will need symbols. So for the runtime itself, and for anything that is statically compiled, like C, C++ code, you can get debug information just like on Windows using debug information files. But for JIT compiled code, you don't have symbols ahead of time. You don't have a PDB file for code which is compiled at runtime. So when you open a recording, you will often see a bunch of addresses, exactly in the places you care about. You will see function names for statically compiled code, but you will not see function names for your C# code, which you care about and want to profile. So the way to address this is to get debug information. And unfortunately, for different kinds of functions, there are different sources of debug information. I have a few examples here. I'm not going to go over them in a lot of detail, but just as an example, again, anything that is statically compiled, you can get debug information from the binary itself or as an additional package, but it is statically available. But for JITted code, for code that's compiled at runtime, you will need the CLR to generate special debugging information. For any method which is JIT compiled, you will need extra information that tells you how to map addresses to function names. And this information on Linux is emitted by the runtime into a bunch of simple text files that sit by default in the temp folder and have a specific pattern so that other tools can find them. And perf, specifically, which I was talking about, can find this information there. Okay, so I've been telling you enough theory. I want to show you an example of actual CPU profiling using these tools. But one last thing I have to tell you is the visualization we will use. And I've been talking about flame graphs on Windows as well for quite a few years now. It's a very useful visualization method for performance information for call stacks. Unfortunately, on Windows, it's not yet gaining the recognition it should be gaining. So I'm going to talk about it very, very briefly, and we'll see multiple examples in my demos. So a flame graph is a way of visualizing lots of stack traces. You have lots and lots of stack traces of interesting things happening in your program, and you want to put them in a single interactive diagram. So flame graphs are a quite popular way of doing this. They were invented by Brendan Gregg, who's a Linux performance architect. And a flame graph is an interactive diagram where each rectangle you see is a function or a method, depends on what you want to call it. The vertical axis the vertical axis is the stack trace. Functions calling each other are shown vertically on the vertical axis. And finally, the wider something is, the more prominent it is, the more time you spent there, for example, the more stack traces like that you had. So basically, when you have a flame graph, you look at the widest things first, and you figure out where you spend your application time. So let's switch to the demo and see how we can CPU profile a .NET Core application running on Linux. I will use a makefile because there's lots of commands to be typing. It's all up on GitHub, and I will share the whole thing with you. So I have this .NET Core application running on Linux. It's a very simple ASP.NET process, which is serving a bunch of different endpoints. And I'll begin by running this auth-bench command, which just uses Apache Bench to multiple times hit one of the endpoints on this ASP.NET application. So it's just running there, sending many HTTP requests. And then I'm going to use the auth record step from my makefile to run a perf recording and collect information for 10 seconds and generate a flame graph. Before we do that, of course, we could use just any Linux performance tool to see just general things like CPU usage, for example. So if I run something like top, for instance, I can see that my Gatos process over here is taking almost 200% CPU. So 2 cores almost completely utilized by this process. I'm just saying it makes sense to profile this application for CPU. So I'm going to run this auth-bench, auth-record step from my makefile. It's running perf, recording for 10 seconds at a certain sampling rate, and then generating a flame graph from the results and uploading it somewhere so we can open it. And notice there are some errors about symbols. I'll talk about it in a moment when we open the resulting flame graph. So just to save us a bit of time, I already have a flame graph, not the same one, but a flame graph open, showing the same information. Just going to zoom in on this a bit. This is where most of my code is. The other areas of this flame graph are not really my code. And you can see, again, each rectangle here is a function, and we should focus on the widest rectangles and the widest rectangles that really belong to us. This is all just .NET code, right? You see Microsoft ASP.NET Core MVC, System Runtime Compiler Services. This is part of the async infrastructure. If I go up a bit, it will eventually lead me to my code. So this here, auth controller post, this is the actual endpoint I was talking to. And this function is responsible for 57% of my CPU time. And then if I'm interested in what it did to consume so much CPU, I can just go up. I can keep going up the vertical axis. And this leads me, for example, to here, which is Microsoft ASP.NET Core Cryptography Key Derivation PBKDF2 Managed PBKDF2 Provider. It's a cryptography API which is running a hash algorithm. So it looks like my authentication controller is spending lots of CPU time in the cryptography API doing hashing. And if I'm interested in what happens there, I can keep going up. And then you see there's lots of allocation-related stuff. So it's not actually even the cryptography work. You see here, there's lots of array allocations and some more array allocations. And let's see what this is here. So this is actually not showing me function names, right? You see system private corelib, system security cryptography algorithms. These are some functions with missing symbols. And I promised I would address this in a bit. So if we go back to my terminal, you can see that perf complained about symbols missing for certain assemblies. So for JIT compiled code, I actually have symbols. For statically compiled code, I also have symbols, but there's also something in between, which is code which is managed, but still compiled ahead of time, right? On Windows, it's engined code. So we have a similar thing on Linux as well. It's called cross-gen, and it compiles C# code to native code ahead of time. And we don't have like easy symbol support for code that was passing through the cross-gen pipeline. I have a script, which I didn't use in this example, which would generate symbols for cross-gen code and merge them back in and sort of make the whole thing work, but it's not a very pretty story right now. So just to let you know, I'm not ignoring this. I'm just not going to spend the 25 minutes explaining this now. But I have all the information for you if you'd like to check it out. So we have a flame graph showing CPU utilization in a .NET Core app running on Linux. We didn't do any extra preparation, except one little thing. When I launched my .NET application, I used an environment variable here called com plus perf map enabled equals 1. And what this did is tell the CLR, tell the JIT compiler, that it has to generate the symbol information for me. If I don't turn on that environment variable, I will not get symbols for JITted code. And you can actually see where this symbol file is if I just go ahead and look at my temp directory. So there is a file there called perf-theprocessid.map, which has mappings between function addresses and function names. And this information is necessary if you want to see function names for JITted code. So among other things, you would have to set this environment variable, or you will only have partial function names in your results. I have a checklist at the end of all the different things you need to remember if you want to do profiling successfully. So this was a quick example of CPU profiling, but there are other interesting things as well that we might be interested in. And before we go there, I just want to show you briefly an alternative to the perf approach of doing things. The perf approach of doing things, as you remember, relies on a file. We record lots of events into a file, and then we analyze that file later. The file can grow pretty big, which makes it not quite appropriate for high-frequency events or for continuous monitoring. If you want to do profiling for an hour and then look at the results, you will not be able to record to a file and then open the file. The file will be bigger than your disk, and you will not be able to open it. So there is an alternative on Linux coming up over the last few kernel releases, which is called BPF. And I wish we could go into more detail about BPF itself. But what you need to know, which is critical for us here, is that BPF presents an alternative to recording every event into a file, where the perf approach is writing every single event to a file and analyzing that file later. The BPF approach is you do the analysis in the kernel where the events occur, and you don't write anything to a file. Instead, you have an in-memory data structure which you share with user space, which you share with the user application, and visualize that data structure. So you don't record every single event into a file. You do the aggregation in the kernel, and you only share the result of that aggregation with user space. And this allows for continuous monitoring. You can run for hours like this because you're not accumulating more and more events. And this allows for much higher frequency event collections. You can have events happening at a rate of millions of times per second, and it will still kind of work because you're not trying to write out something to disk millions of times per second. So we're going to use a few tools based on BPF as well. Perf doesn't use BPF. We're going to use a few tools based on the BPF technology. And the tools I'm going to be showing you are part of a tool collection called BCC. I am one of the contributors, and there's people working on it from Facebook, VMware, PlumGrid, Netflix, a bunch of other companies as well. These tools are used across different platforms and systems. For example, they are deployed across all the Netflix production instances, a lot of the Facebook production instances. So they are quite mature. And there are tools in this collection for looking at a lot of different aspects of Linux systems performance. The tools I'm going to be showing you are just a handful, really, and there's a lot of more useful stuff that we could look at by using these tools to investigate our system. So let's take a look at a slightly different scenario. The events I want to trace are going to be slightly different. So I'm just going to run a different benchmark. Let me first show you what the code is, get stats bench and get stats record is what we'll be doing. So I'm going to run a benchmark against a different endpoint called stats. Let's start this first. Get stats bench. So this is running and just hitting that endpoint with lots and lots of requests. And then what I want to do first anyway is get an idea of how many garbage collections I'm having in my ASP.NET application. Now, on Windows, it would be really easy because we have performance counters for garbage collections. But on Linux, with .NET Core, we actually don't have performance counters. So to extract information about garbage collections happening, I have to use a slightly more hacky approach. I will trace a function in the CLR itself, which is called this, ZN3 SVR6 GC heap 24 garbage collect generation EJ9 and so on. This is just, this is the C++ mangled name of a function that actually had a normal name in C++, but this is a function inside the CLR which is starting a garbage collection. So I'm going to trace that function and just print a message whenever that function is invoked. So that's not super interesting. It just prints a message to the terminal whenever there is a GC in my target process. This is fairly inexpensive. There is no data which is being written to files or anything like that. It's not actually using BPF yet. It's using a different technology. But this is fairly low overhead and replaces performance counters for me as a hack. So you see there are quite a few garbage collections going on. And that leads me to the next thing. I want to try and understand where the allocations in this process are coming from, where this process is actually allocating memory. So for this, we will use BPF-based tools. So I have this other step called alloc count. Let's take a look at this one. And in this step, we will be using a tool from BCC called func count in order to count the number of invocations of any function inside the CLR which has new in the function name. And there could be many functions, so doing this sort of thing, if you record every event to a file, would be quite expensive. But the way BPF works is we're not going to push events to a file, we're going to count them in kernel quite efficiently. So let's see what it looks like. I'm going to run that alloc count step, and it records for 10 seconds all invocations of any function that has new in its name inside the CLR, and there's 96 functions like that. And then at the end, it prints out the number of invocations. And you see, there's a lot of functions that got called which have new in their name. Specifically, there were 3 million invocations of this function here called git new p21 core info class struct and so on. This is a function which allocates. And another one here, string object new string, blah, blah, blah. It's also probably a function that allocates. So you can see just at a very basic level the number of allocations that I am performing. And these are all JIT helpers invoked by the JIT when you use the new IL instruction. But then I also want to understand which code these allocations are coming from. Not just count the number of allocations, but show you which stacks in your process are allocating lots of objects. So in this case, instead of just using the tool func count, we're going to use a similar tool called stack count, which performs stack aggregation. It looks at the call stacks for the event that you specify, and then tells you which call stacks occurred frequently. So it's like a profiler, but not for CPU. It's a profiler for allocations, right? So let's run this step in my makefile. And this uses stack count for 10 seconds, and then creates a flame graph of the results. So that instead of looking at a lot of stack traces in the terminal, we will just get a flame graph that shows us which stacks are allocating lots of memory. Again, it's kind of a hacky approach, but it's very bare bones. There's no dependencies. I didn't have to work very hard. Just traced a bunch of functions in the runtime, And again, just to save us a bit of time, I generated the flame graph in advance. And this is what the flame graph looks like. Again, it starts at the very bottom with a lot of low-level stuff we don't care about. Lots of, again, async infrastructure calls. But for example, this is the actual endpoint that we were talking to. So stats controller get is the endpoint I was hitting with all my HTTP requests. And you can see it was allocating quite a bit. But there is also this stack, which I might have not noticed otherwise, which is coming from, as you can see here from the function names, coming from newtons of JSON. So JSON text writer is allocating lots of stuff as well. During this benchmark, I am returning JSON results, so that's also doing a lot of allocations, not even from my code, but from the ASP.NET Web API infrastructure. So this is, again, very, very simple, bare bones allocation tracing, allocation profiling, get an idea of how many allocations you are performing, get an idea of where these allocations are coming from. That's one use case for BCC, and it's very low overhead data collection. I want to show you a slightly different scenario. So I have another benchmark that we're going to use called cats bench. And this one, if we look at the makefile again, cats bench is talking to another endpoint called API/cat. It's getting some information about cats, supposedly. And if we look at CPU usage, unlike the previous examples, CPU usage here is quite low. So that Gatos process is not doing lots of CPU work. But on the other hand, the requests are quite slow. So I only completed 300 requests so far. So it means it's not a CPU-bound endpoint. It's doing some kind of I/O maybe, waiting for a database, waiting for something. So instead of using a CPU profiler, we'll need to use a profiler that can profile blocked time, that can profile off-CPU time. Guess what? We have a tool in BCC which is called, let's just quit the top window, which is called off-CPU time, which profiles off-CPU time. So first, this command here runs pidstat just to show me the CPU usage of my process, and it's 7% pretty consistently, and then 8 and 6 and that sort of thing. But then it runs off-CPU time, which is a tool that records any blocked time my thread has whenever my thread is not on the CPU, and then generates a flame graph of that to show me where my process is blocked off the CPU. Again, to save a bit of time, I have that flame graph generated ahead of time. This is a flame graph across the whole system. So it's showing, actually it is a flame graph of just my process, but it's a flame graph across all the threads. So it's showing all the blocked threads, not just my ASP.NET application thread. So just as an example, there is this thread over here, which is running Kestrel code. Kestrel is the ASP.NET Core web server. And if you look here, you might have heard that Kestrel on Linux is based on libuv, and that's a library that Node.js also uses for asynchronous networking and I/O processing. So this is basically a thread which is sitting there inside libuv, waiting for something. I don't really care about this thread. The rest of the code here is not even managed. But this thread here, if we keep going up a bit, this leads into my code. Specifically, this guy here is, if you look at the tooltip, it's actually kind of hard to read otherwise. So this is cat controller, cats available. This is a function in my application which got a cat request object, apparently. And this called cat availability service get available cats. And then I had blocked time going into two different places. The first one is going here. And this, if you look at the function names, this is trying to acquire a lock, trying to acquire a managed monitor. So a lot of my wait time is waiting for a lock. And if you look on the right, the other kind of waiting I have is just sleeping. So I also have a bit of sleeps in there. So this getAvailableCats function, some of the time it had to wait for a lock, and some of the time it was just sleeping for some reason. But this is how the blocked time is distributed inside this application. So we have now profiled not just the CPU time, which is my first demo, we have now successfully profiled the off-CPU time as well, whenever we wait and block for something. And this is something you can also do on Windows, but on Windows, if you do this using ETW, it actually works kind of like perf, and you would have to record lots of things into a file and analyze it later. On Linux here, there is no file. The approach we used is completely in kernel, all the aggregations happen in the kernel, and there are no file writes, no I/O at all, while the performance tool is running. Which means you can do this sort of thing not for a few seconds, but for 10 minutes, for an hour, for a week, theoretically, and still get a reasonable amount of data as a result. So this is quite interesting and powerful. In fact, this is more powerful than what you can do on Windows, which I guess in a way could be a bit surprising. But it's not really thanks to .NET Core. It's more thanks to the Linux kernel, really. So this was an example of using some low-level tools to trace various aspects of a .NET Core application. Last thing I want to talk about in the performance part is various runtime events, like garbage collections, JIT compilation, assembly loading. On Windows, these things are using ETW. But ETW is event tracing for Windows. So there is no event tracing for Linux, unfortunately. ETW is actually a Windows kernel feature. And Linux doesn't have exactly that sort of thing. So Microsoft chose to use a library called LTTNG. LTTNG stands for Linux Tracing Toolkit Next Generation. It's a fairly new but also quite stable tool, which is not part of the OS, but it can be installed on pretty much any meaningful distribution. And the way LTTNG works is actually kind of similar to perf. So there is a kernel module in LTTNG which can receive various kinds of events. And there is also a user space component which can receive kinds of events. And the events can go to a memory buffer or to a file. So the file can be processed later. The memory buffer can be processed in real time. That's kind of the architecture. Not really surprising. Pretty much all the performance tools work in a similar fashion. So LTTNG and ETW are actually similar in a lot of ways. So let's take a look at some of the LTTNG events, which are produced by the .NET runtime on Linux, and how to record them. So I'm going to use a benchmark which we already saw, the getStatistics benchmark, which, if you recall, generates lots of allocations, lots of GC pressure. But now, instead of recording the GCs just ad hoc by tracing a bunch of functions in the runtime, I am going to use the official approach, which is the GC events. So going back to my makefile, let's find the LTTNG commands. So you can see why I use a makefile, right? I didn't want to be typing all of this stuff in front of you. So LTTNG, which we use here, is a command line tool for recording these events. And you can see we create a new trace session. We add a bunch of events to it. We record for a few seconds, and then we stop the recording and close the session. It's again very, very similar to ETW on Windows. If you look at the concepts, the session, the providers, the events, it's all quite similar, but not exactly the same as on Windows. So let's do a recording. This is just recording all the specified events for 10 seconds. Let's just look at the list of events for a bit. So GC start event, GC end events, makes sense. GC heap statistics, which is an event generated that tells me the sizes of my generations and that kind of thing. GC allocation tick, which is an event that gets generated every 100 kilobytes of allocated memory. So it's like sampling for memory allocations, not every allocation, but every 100 kilobytes of allocations, I get an event. And lastly, we have GC triggered, which is for when you call GC collect. When you force a garbage collection, we also want that event to be recorded. Okay, so we had a few collections and we had our recording complete. Now, I'm going to use the gcview command, which simply prints all the events in my trace to the terminal. I'm not actually going to run it completely because it's quite long, but just to show you the first few lines. Each line here is an event that got collected by LTTNG. And for each event, you can see we have the CPU ID, the process ID, the thread ID, the event that actually happened, and some additional information. The total number of events that got recorded is 17,000. So again, the way I did it here is the events actually go into a file. So keep in mind the overhead all the time. Keep in mind we're talking about recording lots of events to a file and analyzing them later using this approach. And let's see if we can find some interesting events. Like let's find GC start events and take a look at some of them. So here are the first two GC start events. It tells me again the process ID, the thread ID. I know it's a GC start. The depth here is the generation that is being garbage collected. This is something you can find in the documentation for these events. What each field means, you will find online. So let's see how many garbage collections we had. 45. And we could maybe do an additional grep step, which would look only for Gen 2 garbage collections and count those. Well, turns out all of them were actually Gen 2 garbage collections. So you know, we can do like very, very basic analysis like this. We can also do, and this is a slightly longer command, so I'm not going to type all of it myself. This, let me just show you the command itself. Right over here. So again, we just printed all the events, and then I looked for all the GC allocation tick events. Again, these are the events generated every 100 kilobytes of allocated memory. And then I filtered out the type name being allocated out of the event. And then I sorted and counted the number of occurrences of each type and sorted again. And the result is the number of times I have seen a particular type being allocated. So this is like a very, very rough allocation profiler. It doesn't trace every allocation. It traces samples every 100 kilobytes. But it does tell me at the end, you allocated lots of strings, and also you allocated lots of XML elements. And this is maybe surprising. I'm not sure I would have seen it otherwise, but turns out I'm allocating lots of XML elements as well. So this is recording the CLR events. Again, these events are coming from .NET Core itself, not from the Linux OS. Recording them, visualizing them in a very basic way. If you look online, at .NEXT in Petersburg, Alexey Vereshchagin did a talk on a tool they built for Samsung for doing .NET Core profiling on ARM systems, and he actually built a very simple script which generates plots like this of .NET Core memory usage using the GC events. He just records LTTNG events, and then he gives you a plot like this of .NET memory usage over time. So, you know, we don't have performance counters on Linux. We do have to work our way around it. We do have to find some alternative hacks, but it's absolutely doable. We have all the same information available if we need it, and we can, for example, give you a chart of .NET memory usage over time, show when garbage collections occur, and so on. So this is, if you're interested, he did a talk which was recorded, and it is online. So this wraps up my profiling examples. I've shown you how to profile for CPU time, blocked time, memory allocations, garbage collections. There's lots of information to process, record, and analyze. I want to talk briefly about core dumps as well, because this is kind of, again, the only way to do production debugging of .NET Core applications on Linux today. So we have to understand what's possible, what's doable, how it works. First, just terminology. A core dump or a dump file on Windows is a snapshot of a running process. So we have a process running over time. We stop it for a moment, record it to a file, and then the process keeps running. Now, you can generate core dumps when there is a crash. So if your process is shutting down because of an exception, you can get a core dump to be created. This is the original use case for core dumps and for crash dumps on Windows as well. You can also generate core dumps on demand. So you can take a process which is running successfully, stop it for a moment, generate a dump, and let the process keep running. So how do you actually analyze these dumps? On Windows, as I'm sure a lot of you know, you can use Visual Studio. You can take a dump file, drag it into Visual Studio. Even if it was taken on a different machine, you can drag it into Visual Studio, and Visual Studio shows you what happened. Shows you all the threads, all the code which is running, all the variables, the source code, and so on. Unfortunately, you can't drag Linux core dumps into Visual Studio. I mean, you can, but nothing interesting will happen yet. Visual Studio can't analyze Linux core dumps currently. So the alternative is, and before we get there, I just want to explain how to create core dumps. So before we get to the tools, to create core dumps on Linux, when there is a crash, you need a couple of configuration settings. The first one is a global system variable called core pattern, which specifies, I think the battery on my clicker died, oh well. So core pattern specifies the name of the core dump file to generate, or the tool to use when there is a crash and you would like a core dump to be created. And there is also a per process limit that you would need to shift in some cases for the maximum size of the core dump. In some distributions, that limit is 0. So that even if you do configure a file name for the core dump, you would not get a file because the maximum file size would be 0 bytes. So these are just two things to keep in mind for actually getting a core dump when there is a crash. And if you want to create core dumps on demand, the tool a lot of people use is gcore, which is a very, very simple command line tool. You point it at a process, creates a core dump for you. Okay, so now what? What do you use instead of Visual Studio to analyze these files? So we don't have Visual Studio on Linux quite yet, but we do have the Microsoft-endorsed debugger for this, which is LLDB. LLDB is an open source debugger, which is part of the LLVM project. It's used widely on Macs, not so widely on Linux actually, but it's definitely there and it works. And LLDB in itself can open core dumps in a quite simple way. You just give it the executable name, which crashed, and the core dump file, and it opens it, and for example, it would show you the call stack. And here's what the call stack looks like. It looks almost good, except the few functions in the middle, which is the stuff that we care about. These are the managed functions. This is the C# code. Everything else, like the core CLR stuff, we can get symbols for, because remember, it's statically compiled. But for the dynamically compiled stuff, LLDB doesn't have the information for showing function names. So what do? Microsoft provide a plugin for LLDB, an extension, if you will, which is called libSOS plugin. And if you're familiar with the Windows side of this, on Windows we have WinDBG, which is a simple command line debugger. It actually has a UI, but it's mostly a command line debugger. And we have the SOS debugger extension, which is provided by the .NET installation. Likewise, on Linux, we have LLDB, which is a general command line debugger. It doesn't understand .NET code, but we have a plugin called libSOS plugin, which does understand managed code. By the way, libSOS plugin and SOS on Windows, they share the same code base and the same commands. So if you already know SOS, you also kind of know libSOS plugin as well. Same commands with very few exceptions. LLDB, however, has completely different commands from WinDBG, of course. two completely different tools, so you will still have to learn a few new things. So anyway, you load that plugin into LLDB, and then you can go ahead and run all your favorite SOS commands. I'm going to show you a quick example, and you'll see along the way not everything really works so easily, but it can definitely be accomplished eventually. So for this example, just before I actually run anything, I want to explain. I'm going to run that same .NET process in a Docker container, and I will do the dump analysis in a Docker container as well. And the reason I'm doing it is that basically you will need the exact same version of operating system binaries and libraries as you had in the production environment in order to analyze the dump file successfully. On Windows, we have the Microsoft Symbol server, which can be used for grabbing debugging information. But on Linux, there's not really a public symbol server for all the different distributions. So the easiest way is just to analyze the dump file in the exact same environment as your production process was running in. And the easiest way of doing that is with a Docker container. So I can run the process in the Docker container, and then if there is a core dump, I will create another container with exactly the same version and distribution and analyze the dump file in there. So this is why I use this approach here. So let's take a look at how this works. I'll show you the make file first and then actually run the whole thing. So first, to run the application in a container, there's nothing super interesting here which is related to our topic. So I build a container which has the .NET runtime inside, and then I just run the managed application, the Gatos application in it. Maybe just one tiny interesting thing, which not sure everybody knows. .NET Core on Linux can generate self-contained deployments. So you don't need a shared .NET installation on that machine. You can take pretty much a bare bones Ubuntu image or CentOS image or Fedora image and just copy a directory over to that machine and run the .NET application from that directory. So you can get a completely self-contained directory or archive which has your .NET application, the CLR, and all the dependencies inside. So this is the approach I'm using here. If you look at my Docker file later, you'll see it doesn't install the full .NET distribution. It only installs very basic Linux tools and just copies a directory on top of them. So we run in a container, and then the analysis, I use a different container, but based on the same image, more or less. And you'll notice that the command I run in the container is going to be LLDB with a bunch of additional arguments, such as loading that plugin and so on. So let me demonstrate the whole thing. First of all, here, I'm going to run the application in a container. And it's running. That Gatos container is up. And then I'm going to crash it. I have a command which will crash. I have an endpoint that will crash that container. And it takes a few seconds. So basically, the crash happens in the background, which is kind of interesting. So the original request returns, but then a few seconds later, that process crashes. And if we look at the logs for that container, you'll see that there is an unhandled exception at the end. And there's even actually a call stack over here, which prints the exception information, the call stack of that exception. So let's open the core dump that got generated. Sorry, I have it in my make file. So this copies the core file into a volume that is shared with the container, launches LLDB in the container, loads the SOS plugin into the LLDB instance, and then I can type SOS help, and it prints a bunch of SOS commands. And if you remember this from Windows, it's the same commands. Again, more or less. There's just a few exceptions which are not available on Linux, but most SOS commands are actually there. And so, for example, there is a quite useful SOS command called print exception, which prints the details of the current managed exception. Oh no, the current thread is unmanaged. How about the stack trace? So it's actually CLR stack like this. Oh no, it's not a managed thread, unable to walk the managed stack. Now, if you look here, this looks a little suspicious. It says OS thread ID 0, and then in the parentheses it says the number 1. So the 1 is actually the managed thread ID, but the 0, the OS thread ID 0, that doesn't really make sense. On Windows, there is no thread ID 0. Well, actually there is, but not in a standard user process. And on Linux also, 0 is not a valid thread ID. So something's weird here, and turns out LLDB and that SOS plugin, they can't map debugger thread IDs and managed thread IDs to operating system thread IDs automatically. It's something you have to do, which is like, what? I'm supposed to tell the debugger which thread IDs match the managed threads in my application? Yes, you are supposed to do it. So I'm not going to do it right now because we only have a couple minutes left, but I have a little script that does it automatically, because if you have 500 threads, mapping each one is going to be quite painful. So I'm not going to do it now. Instead, just to save us a bit of time, if we look at the list of all the threads using the threads command in SOS, then you will see that the first thread is the one that had the exception, and it tells me at the end what the exception was, so shutdown exception, and it gives me the exception object's address as well. So I can use this address with the print exception command to start my investigation, to get at least some basic information about the exception that happened. And you can see here it was a shutdown exception, and the call stack for it was quite interesting because it came from task scheduler published unobserved task exception. And you can investigate it later if you'd like, but this happens when you have a task which throws an exception, but you don't observe that exception, and then the task object gets finalized, and that exception would crash your process. So we actually have all the exception information available, and we could look at the other threads as well, the other stacks as well, if we tell the plugin how to map the thread IDs, which is kind of annoying. It's not as friendly as dragging a dump file into Visual Studio, but it's mostly functional and it mostly works, as you can see. Again, please do remember you need the very exact same environment. You do need all the operating system libraries to be identical, and of course the .NET version to be identical as well. So let me wrap up real quick. I have this little checklist on the slides which you should look at later. These are all the things you need to enable so you will be able to do a successful performance and debugging investigation. Check it out later. I've shown you examples of allocation profiling, generating flame graphs, tracing all kinds of runtimes events like garbage collections and allocation sampling, that kind of thing. I have a bunch of references that you can look at later, including a few blog posts I've written which cover more or less the same material. The slides are here, the demos are here. I'll be in the discussion zone to answer any additional questions, and enjoy the rest of .next. Thank you very much.